Today we're going to revise logic gates, first of all, and, or, and not. Let's take a look at AND first of all. I'm going to write out its so-called truth table in my own way, which might be slightly different to the way other people lay it out. I like to lay these things out as in a sort of square matrix. Let's call here on the left input A into my AND gate, and up at the top I'm going to talk about input B. It has two inputs and one output, and the output from the gate is represented inside this square area here. So the A input, we're working in binary as ever, can take on values of 0 and 1, so can B. Okay, AND is very simple. It says the outcome is true, which is normally denoted by a 1 nowadays in binary. The outcome's true only if both of the inputs are true. Of course, that's what AND means in English. That must be true and that must be true. So let's do 1 and 1 first of all. 1 and 1 is like true and true. Yes, the outcome is true. But if you take 0 and 0, given that 0 means false, then the AND can't be true because you're saying it's false and it's false. So the outcome is false. It's a 0. And equally, if one of them is true and one of them is false, the outcome still is false because the outcome of an AND gate, for it to be true, both of them have got to be true. So you end up with a result matrix here, look, with 3 zeros in it and only 1 1. Now, just this once, I won't do it for all of the others, but just this once, I shall say, feel free to write it down like this, with an F and a T, standing for true and false, but it's still the case that under AND logic, for the outcome to be true, you must have a couple of true inputs here. So that's exactly the image of that, using F's and T's rather than 1s and 0s. If you're an electronics engineer and you're building some electronics to do these logic functions, what you would draw is your AND gate with two inputs, A and B, one output, and yeah, the thing to remember is that the AND is a fairly rounded kind of shape at the front, but the point here is that the outcome of doing A and B together can be written in lots of ways. You could write it as A and B. Sometimes if you look in logic textbooks, you'll find that they use a thing looking like a little spike down on the baseline. That is the mathematical logician's favoured way of saying AND, but it's the same thing as writing A and D. Very occasionally you'll also see A dot B. That dot is like the one that some of you would have been taught at high school to denote multiplication, rather than using the multiply symbol. It was noted early on that AND is a bit like doing multiplication, because if you say, what happens if I just multiply the two inputs instead of doing this AND nonsense? Well, 0 times 0 is 0. 1 times 0 is 0. That 1 multiplied by 1, 1 times 1 is 1. You get the same outcome there as if you'd been multiplying the 1s and 0s with each other. And that is why AND is sometimes called logical product. Okay, now we've got the notation established, we can go ahead fairly quickly now on the other possibilities here. Let's take a look at the OR gate. Well, for this, which is the so-called inclusive OR, if you want to give it its full name, the rule is that the outcome is true if either or both of the inputs are true. One inclusive OR with 1 or 1, well, they're both true, so the outcome's true. 1 ORed with 0, if either one of them's true, the outcome's true, so you put a 1 there. Similarly, 0 ORed with 1, well, one of them's true, so the outcome's true, and only 0 ORed with 0 gives you a 0 or a false. So it's called an inclusive OR because it includes this situation here where they really are both true to start with. Writing it down in what an electronics engineer likes to see, here you come, fast back, go faster, tail fin there, and it slopes round like this. There is your OR gate with an A and a B inputs. Here comes the output, and again we can either write it down as A ORed with B, or we could say A. Notice it's the opposite way round to the and that looks like a little V on the baseline. So you can write it like that. Or many people noted very early on when studying mathematical logic that OR does more or less behave like addition. Not quite. I mean, look at it. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1, really, referring back to the binary adder video I did a week or two ago, 1 added to 1 should really put down a 0 and carry 1. But here, it's as if the carry bit's retained and held inside. But as far as logicians were concerned, a lot of them like to call this the logical sum, whereas AND is the logical product. To complete these three, there's a very familiar indeed now, there is a very special one, and that's our good old friend NOT. It's special in that it doesn't take 2 operands, it only takes 1 operand. NOT is a simple inverter. Give it a 0, it'll turn it to a 1. Give it a 1, it'll turn it to a 0. So we've only got one input, let's call it A. What's the outcome? Well, the outcome is a single column now. It's not a square, because what you're saying is if you apply NOT to 0, you get a 1. If you apply NOT to 1, you get a 0. It just flips it. Simple as that. And the circuit diagram, electronicsy type notation, which is a triangle with a little circle at the end. And what comes out of here? Well, there's lots of ways of writing NOT A. You can write it as NOT A. Sometimes you'll see it written as twiddle A. Sometimes you'll see that some logicians like to use a thing like a sort of bent crowbar to denote NOT. So that can also be used to call the output NOT A. Those three taken together are what are called logically sufficient to do anything you want in logic, and, or, and not taken together. Dr. Heartbleed, bless his cotton socks, has done even more advanced stuff with you now, which I'll just mention. If you want to glue a NOT gate onto the output of an OR gate, say, so you do the inclusive OR, but then the moment you get its result, you flip its direction, you turn it over. Instead of just taking that and gluing it onto there, you're allowed to abbreviate by putting the circle on the end of the OR gate. It's still got the A and B inputs, and it's still got an output, but notice the moment you do the OR, you turn it the other way around. That's what the circle says. So that is a NOR gate. And I know for a fact that Dr. Bagley has done that with you in one of his videos.
We'd like to thank Audible.com for sponsoring this computer file video. They've got over 100,000 titles to choose from, and if you'd like to try one out for free, go over to audible.com/computerfile. Today I'd like to recommend Red Mars by Kim Stanley Robinson. There's been a lot of hype recently about visiting and colonising Mars, and Kim Stanley Robinson really captures what this might be like to do. It feels very realistic, not the sort of utopian vision you get in some science fiction. So check out Red Mars, go over to audible.com/computerfile, try it out for free, and thanks once again to them for sponsoring this computer file video.
It would be useful to refresh our memory of how a NOR gate works. So that's our NOR gate, and it has 2 inputs, which we'll label as A and B.